Today I want to introduce hypothesis testing in one of the most simple and basic settings. And this really simple case would be when we have two groups, such as an experimental group and a control group, such as cases. A case is somebody who has a disease, compared to controls. A control would be somebody who doesn't have the disease. So those would be your two groups, cases and controls, and you'd compare them to see if there are explanatory variables that could explain some of the variability in why certain people get a certain disease and other people don't. We could also look at people who are exposed to a risk factor, and we could look at people who are not exposed to a risk factor and see if that is linked to whether or not they get a certain disease or condition. So the feature here that really links these two ideas is that there are two groups, and only two groups. And the experimental and control group is something that you're probably used to even from high school. And so that's one of the most simple cases of hypothesis testing that you can really have. So with this really simple idea, we also have a really simple research question. And that question is there a link between this and that? It's about as simple as you can get. Now let's talk about links. There are two types of links that you are responsible for in a college-level statistics course. One type of link is called an association. And you could say, for example, there is an association between this and that. For example, we might want to test whether there's an association between vaping and asthma. I'm not saying there is. I'm saying it's something we could theoretically test for. We might want to test whether vaping causes asthma. And that, of course, is a little more tricky to do. But it is certainly possible to design such a study, though may not necessarily be ethical in the case of vaping. So we're saying, is there a link between this and that? But what is the this and what is the that? So in college-level statistics, the this is most often called the explanatory variable, and the that is most often called the response variable. Now, it turns out that the response variable is really the thing you're interested in. For example, let's say we're interested in diet and cancer. So we might be interested in asking ourselves, why do some women get breast cancer and others don't? And of course, there's genetics, there's environment, and there's the interaction between the two. But consider, hypothetically, broccoli consumption. There was a nice study in the Journal of Clinical Nutrition on broccoli consumption and breast cancer. So could broccoli consumption explain some of the variability in why some women develop breast cancer and others don't? The amount of broccoli consumption could be an explanatory variable. The response variable would be breast cancer, and that's the thing we're really interested in. We're interested in explaining the variability in another variable, and that's called the response variable. And in stats, it's a good idea to always think about this idea of variability. Why do some people experience this and others don't, right? And maybe I really should have said that. Why do some people experience that and others don't? Because the that is what I'm calling the response variable. But again, this is really, really simple. Is there a link between this and that? I mean, how much more simple can it be? Now, the explanatory variable is sometimes called an independent variable, but only in experiments, designed experiments. And that's a situation where the experimenter actually manipulates, the subjects in various ways. And it's not proper to use the term independent variable in an observational study where there's no experimentation done. The same thing with the dependent variable. Sometimes the response variable could be called the dependent variable, but only in the case of experiments. So this is a distinction that really should be kept in the foreground of your mind. And sometimes this explanatory variable is also called an exposure variable, and the response variable may be called an outcome variable. So this is the basic, one of the most simple hypothesis testing paradigms is there a link between this and that? Now, I haven't yet mentioned the hypothesis. In high school, they may have defined the term hypothesis as an educated guess, and that might be okay for high school, but it's not okay for college. That's a horrible definition of what a hypothesis is for college. And the reason why that's such a horrible definition is because in a college-level hypothesis testing scenario, there are actually two rival hypotheses. One hypothesis is called the null hypothesis. And the null hypothesis is symbolized by a capital H with a subscript 0. And the null hypothesis is some variation on the theme, there is no link between this and that. And I'll put this in quotes, and I'll put that in quotes. And in college level stats, the this is usually the explanatory variable, and the that is usually the response variable. Now, I told you there were two hypotheses. The other hypothesis is called the alternative hypothesis. The alternative hypothesis. And I'm just using these these are called ditto marks. I don't want to write the term hypothesis over again. So I'm just using these ditto marks. And the alternative hypothesis is symbolized with an H with a subscript 1. But some people will use a subscript A. Some people don't even use H1 or HA. They might use a whole different letter like K. It doesn't matter. You know, a rose by any other name would smell as sweet, allegedly. No evidence to prove that. Just kidding. So the alternative hypothesis says there is a link between this and that. Right? The alternative hypothesis says there is a link between this and that. So I hope now at the college level you could see how crazy it is to define a hypothesis as an educated guess, because let's say one of these hypotheses was an educated guess. Let's say the null hypothesis is that there's no link between vaping and asthma. Well, the alternative hypothesis, which is necessary for a statistical hypothesis test, says there is a link between vaping and asthma. And so if one is an educated guess, the other is the opposite, but they're both hypotheses. So that's why, you know, maybe your high school teacher could get away with calling a hypothesis an educated guess in high school, but in college it's a horrible definition, and please try to purge that from your consciousness if you can. So I want to continue along this a little bit. There are a couple of other hypothesis testing terms that you do need to know. A type 1 error, and this is Roman numeral 1. It looks like an I, but it's a Roman numeral 1. A type 1 error is the act of the event of rejecting the no, rejecting the null hypothesis when the null hypothesis is true. All right, so if you're rejecting something that's true, if you're rejecting truth, of course, you've made an error, And a type 2 error, Roman numeral 2, and I'm going to use ditto marks again, is the act of failing to reject. The null hypothesis when the alternative hypothesis is true. So if you're in a college level statistics course, these are such fundamentally important vocabulary terms. You got to memorize these cold. So how do you know if you've memorized something cold? Well, you could say it really fast, like a used car salesman on television who would say 9.2% APR, taxes and tags due upon financing. Some restrictions may apply. You know how they can say it really fast, even though they're reading it. But the way you know if you've really memorized a vocabulary term is, if someone says, hey, what's a type 1 error? You should be able to say rejecting the null hypothesis when the null hypothesis is true. Fast, without thinking about it, And, this is going to take a little time, and some students use flashcards, do it however you want. But these are really important statistical terms. Now, some students take issue with college professors using the phrase failing to reject because they say, well, isn't that the same as just accepting? If you don't reject the null hypothesis, will you accept it? And yeah, that's true. But historically in statistics, at least decades ago, statisticians preferred to say failing to reject rather than accepting, because in this language, there's this understanding that models are never true. They're just approximations of reality to some degree, but they're never actually true. And so statisticians, at least in the older times, didn't really want to use the term accept. But I've met plenty of modern statisticians who use the term accept instead of failing to reject. And you're going to have to ask your own professor whether they care about that distinction. I personally don't. If you want to say accept, you want to say failing to reject, it doesn't matter to me, as long as you understand that type 1 and type 2 errors exist and human beings can be wrong. And this is a fundamentally important idea. Now, in college level statistics, these events that can happen, type 1 errors and type 2 errors, these are errors. These events have probabilities that can actually be calculated using mathematics. And so I'm going to let the letter P represent probability. The probability of committing a type 1 error is called alpha. And alpha is a Greek letter. And the symbol for alpha looks like this. It's not a 2. Some of my students, when I write this on the board, they'll say, hey, professor, where did you get the 2 from? And it took me a while to realize that they think the alpha looks like a 2, and so they think it's a 2, but it's a Greek letter alpha, right? It's a Greek letter. And the probability of committing a type 2 error is called beta, and beta is the second Greek letter, this in the Greek alphabet, the second letter in the Greek alphabet. And beta looks pretty much like a B, only there's a little tail. I exaggerated it a little bit. There's a little tail under it, and it's a Greek letter. Now, I do want to call your attention to one little thing. And that These curly brackets here, right? These are sometimes called set parentheses. And you put events in probability and statistics, you put events inside these set parentheses to show the reader that, it's an event. So we can read this as the probability of committing a type 1 error, or the probability of the event of a type 1 error manifesting in reality. So this is, statistics, like any other academic discipline, has its own jargon and its own notation and its own symbolism. And, some people are, a little bit intimidated by that. But, as long as you go through it slowly and you memorize these things, it's really not the worst thing in the world. So alpha is the probability of rejecting the null hypothesis when the null hypothesis is actually true. And that's an error. We want this thing to be as small as possible. And a type 2 error is failing to reject the null when the alternative is true. And beta is the probability of failing to reject the null when the alternative is true. So these are probabilities that are calculated. And the subject of statistics has evolved so that there are standards for these two probabilities. Now, I want to point out that these are error probabilities, right? So, nobody in their right mind would want to make an error, right? Who on earth would want to make an error? So we want these things to be low. And in the real world, alpha is typically 5%. And the reason for that is one of the founding fathers of statistics, a guy named Fisher, Ronald Fisher. He said, kind of glibly, that 1 in 20 seems like a good number, and 1 in 20 is 5%. And most statisticians suspect that, even though it seemed arbitrary, there was actually a good reason why he picked 5%, why he picked 1 in 20. He just didn't tell anybody the reason, because sometimes people will be persuaded more by arbitrary than they will by a reason, if the reason doesn't really find purchase in their consciousness as to how they, see the world. And that's, if you stick with me on this channel, I'll explain to you where I think the 1 in 20 came from. And I think he had really good reason to pick the 1 in 20. That's just my opinion. So this is pretty much the gold standard. Alpha is usually set to about 5%. But sometimes alpha is equal to 1%. Sometimes we want a higher standard. So in the real world, you'll see alpha values of 5% almost always, but sometimes this 1% higher standard is used. And beta is often 20%. Like, if you want to apply for, like an NIH grant, and you want to show that you have a sufficient number of study subjects so that your beta, your probability of committing the second type of error, is 20%. You can often get the grant based on, having enough subjects to have a beta of 20%. Of course, 10% would be nicer, but you can usually get away with with around 20%. You know, it depends on the circumstance. The beta value is not as accepted as the alpha value, but this alpha of 5% is, this really has found its place in science, all because R.A. Fisher said 1 in 20 seems like a good number. So the other thing I want to sort of go about is what happens if we reject. Now I'm just going to write REJ for reject. I'm going to save myself a little writing. What happens if we reject the null hypothesis when the alternative hypothesis is true? Now, one thing I should mention, I told you these were rival hypotheses, the null and the alternative. But I could go a little stronger than that. I can say they are mutually exclusive. Mutually exclusive. I'm going to write that down. So the null and the alternative hypotheses are mutually exclusive. Now, that doesn't mean they only date each other. Mutually exclusive means if the null hypothesis is true, the alternative hypothesis must be false. And it also means if the null hypothesis is false, the alternative hypothesis must be true. That's what mutually exclusive means. So if you reject the null hypothesis, which is like accepting the alternative, when the alternative is true, you've actually made yourself a correct decision. So this is not an error. This is a correct decision. This is a great thing you've just done, you know? And if you fail to reject the null, when the null hypothesis is true, you've made another type of correct decision. And, surprise, surprise, in college-level statistics, these have terms. So the probability of this correct decision here, rejecting the null when the alternative is true, the probability is called the power of the statistical test. And that's a really important word, power. Power is really important. You guys have a little memorization to do to understand these ideas, but it's really important. And the probability of failing to reject the null when the null is true is called the operating characteristic of the test. Operating characteristic. So I want to close this video by emphasizing and underscoring the genius behind this statistical hypothesis testing paradigm. So we started out, right? We started out with something really simple. is there a link between this and that? And of course, in college statistics, we have terminology for, what kind of link it is and what we call the this and what we call the that. And then what we did was we partitioned our universe into two states of nature, right? The null hypothesis says there is no link between this and that, no link. And the alternative hypothesis says there is a link between this and that. And these are rival hypotheses. Rival, if we say these hypotheses are rival, they're competing with each other in some sense. And what is the competition? How do they score their points? They don't really enter into a ring or an octagon. They score their points by which hypothesis better explains the data. But these hypotheses are also mutually exclusive. That means if one is true, the other is false. If one is false, the other is true. And so by partitioning our universe into these two mutually exclusive states of nature, we now have exactly two types of errors, which we can calculate the probabilities of, and these probabilities are called alpha and beta. How cool is that? That there are only two types of errors. There are exactly two types of errors. And in a Stats 1 class in college, you'll learn how to actually calculate them. High school, probably not. And there are also two types of correct decisions. And we can calculate the probability of those correct decisions. One probability is called the power of the test, and the other one is called the operating characteristic of the test. So we have two types of errors, and we have two types of correct decisions. And this is the most simple hypothesis testing paradigm that we can really introduce these ideas with. Is there a link between this and that? If you've liked this video, please subscribe to my channel and give me a thumbs up. And, tell all your friends who, study statistics or plan to study statistics. And if there's anything about this video that, you feel could be improved, send me a nice, respectful comment, and I will do my best at improving it.